In the previous video, we looked at several examples relating to conservation of energy. Now we will go through how to solve problems relating to conservation of energy. In our first example, we have a wrecking ball of mass 200 kilograms that is released 4 meters above a concrete platform. We want to know what is the potential energy of the ball at the top before it's released. In this problem, we are solving for potential energy. You can look back at your previous notes to see that potential energy is equal to the weight of an object multiplied by its height. We also discussed previously that weight is equal to the object's mass multiplied by the acceleration due to gravity. Therefore, we can say that potential energy is equal to mass multiplied by acceleration due to gravity multiplied by height above your reference level. Our mass is 200 kilograms. The acceleration due to gravity in the metric system is 9.8 meters per second squared, and the height is 4 meters above the platform. When we multiply, we end up with roughly 7,840 joules. In the next part of this problem, we want to know what is the kinetic energy of the ball at the bottom just before it hits the platform. Here, we aren't given the velocity of the ball, so we cannot use our usual formula for kinetic energy. However, we do know that energy is not created or destroyed, it changes forms. Therefore, we can use the idea of conservation of energy to see that the kinetic energy of the ball just before it hits the concrete platform will be the same as the potential energy of the ball before it is released. Therefore, the kinetic energy of the ball just before it hits the platform is also 7,840 joules. Now, we want to find the speed of the ball at the bottom. In order to solve this, we are introduced to one more formula. For any object in free fall, neglecting air resistance, the speed of the object is equal to the square root of the quantity 2 multiplied by the acceleration due to gravity g multiplied by the initial height of the object. Therefore, our speed is equal to the square root of 2 multiplied by 9.8 meters per second squared multiplied by 4 meters above the platform. Multiplying, we should find the speed of the ball is approximately 8.85 meters per second. Our last question relating to the same wrecking ball, when the wrecking ball hits the concrete, where does all of the kinetic energy go? It can't simply disappear because energy is neither created nor destroyed in a closed system. Instead, that kinetic energy might be converted into thermal energy or heat. The ball hitting the concrete is also pretty loud, so some of it might be converted into sound energy. We would also assume that if a wrecking ball hits concrete, it probably breaks the concrete, so the rest of that kinetic energy must be converted into elastic potential energy from the concrete breaking. This concludes our discussion of conservation of energy.